So I have one problem, and it's solve for x, and it's 400 times e raised to the power of 2 times x equals 600.
Okay. Whenever this is an exponential equation, it's not an algebraic one. You cannot solve exponential equations algebraically. You have to use logs. Okay? That's the first thing you need to recognize when you see a problem like this.
Right.
Second thing is that I don't want to take logs until I can get that isolated. Once I can get that isolated on one side, then I could take the natural log of both sides. So
Right.
always the first step here is to divide both sides by that coefficient.
Okay.
Okay, so that gives you e to the 2x equals 3/2. Now, natural log of both sides, that's always a good thing when you see that because that's equal to 1.
Right.
Remember the log base of base. The log base b of b is always equal to 1 no matter what the base is. And by the rules of logs, I can move this 2x now down on the algebra line. So it becomes 2x natural log of e equals natural log of, I'll change that to 1.5 even though I don't really like doing that. And that I can replace with a 1. So now x just becomes, let's change it back to 3/2, which now becomes, no it doesn't. It's the natural log of 3/2 divided by 2.
Okay.
I was going to say natural log of 3/4, but that is not correct.
Right.
The natural log of 3/4 is not the same as what I wrote. In other words, this gives you a number out of your calculator, and then you take that number and divide it by 2, which would not be the same number as the natural log of 3/4. Remember something else about logs. When you take logs of numbers greater than 1, you get positive numbers. When you take the logs of numbers between 0 and 1, you get negative numbers.
Right.
So the natural log of 3/4 would necessarily be a negative number, right?
Right.
Should be, but that's a positive number, and when I divide it by 2, it's still a positive number. So that's just more confirmation that the natural log of 3/2 divided by 2 is not the same as the natural log of 3/4.
Okay.
Now I didn't need to really write this. I could have just said that this entire thing is equal to 2x. I wrote it kind of for clarification there. And with logs, I do kind of prefer working with ratios rather than decimals. Not sure why. I think you end up with some certain log problems that work out a little bit better if you leave them in fractions. Maybe not. Might just be a personal preference. But.
I tend to like the fractions more too.
Yeah, in fact, fractions work better in almost all higher forms of math, especially when you get to trig. Trig is all about ratios, not, you would never give an answer of 1.5 in trig. It would always be 3/2, some ratio of one number over another number. All right. What else you got? And that answer, you obviously need a calculator to come up with that answer.
Right. So if I have f of x equals log of x plus 1 divided by x minus 4.
Okay.
And how would I find the domain?
Okay. Whenever they ask you about domain, what you have to ask yourself is, what can X not be? Well, when you're dealing with log functions, first of all, this can't be 0 or negative.
Right.
Okay? Second, you can't divide by 0. So there's no way that x cannot be equal to 4. That would cause division by 0. X cannot be equal to negative 1. That would cause the whole argument to be 0. And that would mean you'd be taking the log of a negative number. And finally, x plus 1 over x minus 4 has to be greater than 0.
Okay.
That's not so easy to solve for. Are you familiar with line charts?
Maybe not with
Well,
that.
this is a perfect problem for line charts because I have no idea what value of x is going to make this thing greater than 0. Let me show you the line chart technique. Whenever you have an inequality and on the left side you have either a product or a quotient, you're going to need to use this. In other words, even if I had x plus 1 times x minus 4, I would need to use the line chart technique. And here's the line chart technique. First of all, you want to identify your critical points. Critical points are wherever the numerator or the denominator equals 0. So the critical points are minus 1 and 4. Now I'm going to draw a chart, a line, and I'm going to label those points, and only those points. I'm not going to label 0. Now, what I want to do is I want to pick a number to the left of my furthest most point. Pick a number.
Negative 2.
Okay. What's the numerator? Is it plus or minus when x is negative 2?
Minus.
What's the denominator when x is minus 2?
Negative.
Negative divided by negative is positive. Therefore, everything in that region all the way to negative infinity is positive.
Okay.
Now pick a number between negative 1 and 4.
2.
Pick an easy one like 0.
0.
In other words, you could pick 2. I was just saying that whenever you have a chance to pick 0, always pick it because it makes the math super easy. You can't hardly make a mistake. When you have 0 for x, you get a plus in the numerator, a negative in the denominator. That result is negative. Therefore, everything in that range is negative.
Okay.
Finally, you pick a number to the right of 4, like 5. Numerator is plus, the denominator is plus, plus divided by plus is plus. Now you have your solution. In other words, what we're looking for is for that to be greater than 0. Well, that's everywhere where it's a plus. So in interval notation, my solution is negative infinity to negative 1. It cannot be negative 1, so I need a parentheses. In combination, well, you've had interval notation, right?
Yes.
Combination with 4, again with parentheses because it cannot be 4. There's your answer. That's the domain.
Okay.
Long as we're not between minus 1 and 4, we're okay.
Okay.
And that's how you need to do any kind of a problem like that. Even if it was x plus 1 times x minus 4, You still have those two critical points. You do the analysis exactly the same, and you make your line chart, and then you look at your line chart and figure out where it's greater than 0.
Okay.
Which is where it's plus. All right. Another one?
Yeah. I'm sorry. It's a word problem. So
Okay. Now, I did find it useful last night when you sent me pictures of those word problems, just because they were complex enough and had an A, a B, a C, and a D in places, that it was helpful for me to be able to see it. It depends on how complex of a word problem it is, I suppose. If you want to give a shot at verbalizing it, go ahead.
No, I just sent it to your email.
All right. This one didn't go into my spam. I found it very interesting that it went into my spam yesterday. Google's pretty good about not putting crucial emails into spam.
Mm-hmm.
All right, what do we got here? All right. Let's talk about the three different equations. Exponential growth and exponential decay. Okay? Annual compounding. What's that equation?
A equals P times 1 plus R to the power of T.
Greater, let's call it more often than annual. I don't know how math refers to that. I always find it very cumbersome to label. What's that equation?
A equals P times 1 plus R over N to the power of T times N.
Okay. And finally, continuous compounding.
I don't remember this one.
Hurt.
Oh, right, yeah, PE to the RT.
And both the R and the T go in the exponent, which is noticeably different than either of the first two. Because in the first two, the rate goes down here. Same with that middle one. But in the third one, the rate is in the exponent, and that makes all the calculations different. And in fact, I think it was you that we went through a number of problems that are typically continuous compounding. In other words, population growth, bacteria growth, radioactive decay, all of those are continuous. And yet, at that time, I don't think we had gotten the continuous compounding formula yet, so we used the annual compounding. And annual compounding is a human invention. There's nothing in the world that compounds annually except a bank account, only because the bank account does it that way.
Okay.
Everything else either grows or decays continuously. Now, this specific problem, you got two different funds, and Fund A pays a higher interest rate, but only compounds semi-annually. Fund B pays a lower interest rate, but compounds continuously, which is better. The question is how much better? All right. So, write equations for the value of both funds 2 years after 2011. So, Fund A. What's it going to be? First of all, it's compounding semi-annually at a 9.2% rate.
So if V of t equals 15,000 times 1 plus 0.092 over 2 to the power of 2t.
Yeah, n being how often per year it's being compounded. In other words, if it was compounded monthly, then n would be 12. If it was compounded daily, n would be 365. Okay? Now, you can simplify this a little bit, not a lot. In other words, I don't know that this would be the answer you'd want to give. Let's see, if I divide that in 2, I get 0.046, so that's 1.046 to the 2t. And there's your answer. V of t. Now, well, I guess we want to write that V sub A of t. There's the formula for Fund A. And what's the formula for Fund B? In other words, these B's, you can't say V of t for both because they're not the same V of t.
Right.
You have to distinguish them from one another if I'm going to write them together like this. Okay, so the other fund earns 8.5% but compounds continuously. So what's its equation?
15,000 times E to the power of 0.085 times T.
Yeah, and this R is not 1 plus R anymore. It's just R.
Right.
Okay? All right. So there's our two equations, with T being the number of years after 2011. So in 2012, T would be 1. 2013, right. T would be 2. What's the value of each fund in the year 2043? Well, let's figure out what T is.
32.
Yeah. And again, there's a situation where you're never sure you have to add one or sometimes subtract one when you subtract two numbers like that. In other words, is it 32 or is it maybe 33? That's why I said, well, if we know that T is 1 in the year 2012, we get that by subtracting 2012 minus 2011 gives us 1, then I can safely subtract 2043 minus 2011 to get the proper T.
Right.
Okay. So if T is 32, then all I got to do is plug in T of 32 in both of these equations, and what that would look like would be something like V sub A of 32 would be equal to whatever it is. V sub B of 32 would be equal to whatever it is. Let's go ahead and figure that out. You got your calculator?
Yeah.
I'm a little curious as to which one is better. I actually believe the Fund A will be quite a bit better. In In other words,
Yeah, it is.
continuous compounding is good, but not that good. I mean, better, but
yeah, fund day is $39,000.
and you used a T of 32?
Yes.
Okay, so how much is it?
It's for fund A it's 266,759.
Okay.
And then for fund B it's 227,705.
Okay. So the fact we were continuously compounding did not make up for the fact that we were getting 1% less on our money.
Right.
When does each fund total $1 million? How do I solve this? Let's talk about the first fund.
Set both equations equal to 0. Or I'm sorry, so it's 1 to 1 million.
Yeah, in other words, set V sub A of T equal to $1 million. So I start off this way. That's 2T, right? Yeah.
Yeah.
And now I have to solve this.
Right.
Well, this is very similar to the very first problem you gave me, e to the 2x. Okay? So what we have to do is isolate that and then use logs to solve because our variable is in the exponent. First step here.
Divide both sides by 15,000.
What do you get on the left? They couldn't give us a number that was...
It's
They couldn't have made that 10,000? You see why I'm saying?
yeah, it's 200 over 3.
All right, I can work with that.
Not too ugly.
No.
But
Let's see if I cancel. I'm just doing a little mental check here. So I'm taking 1,000 and dividing it by 15, and then I'm going to divide top and bottom by 5. Okay. All right, so that equals 1.046 to the 2t. Now what?
Would you take the log of both sides, or would you...
What kind of log?
Natural log.
Yeah, it doesn't really matter which kind of log you use.
Right.
Natural log, you might as well get used to using it. When you get to calculus, you'll be using it almost exclusively. And these ratios are the same. In other words, if I use common logs, I'm going to come up with an answer here that's a ratio of 2 logs, right?
Right.
What now? Now that I took the natural log of both sides, what am I going to do?
Bring the 2t out in front of the natural log.
Okay, so I got 2t times natural log of 1.046 over there. Now what? Trying to solve for that.
Not divide by
whatever is not that, right?
Right.
In other words, that 2 is a number and this is just a number. So that's a coefficient. So if I divide both sides by the coefficient of t, I get natural log of 200 divided by 3 divided by 2 times the natural log of 1.046. Why don't you come up with an answer for that, just so we'll know it's in the ballpark. It's going to take a while to grow 15,000 to $1 million, although maybe not at that interest rate. That's a pretty good interest rate. 0.92.
46.691.
46.691 years. Yeah, that sounds about right. Okay, and now if we take our other equation and again divide both sides by 15,000. So on the left I'm going to have 200 divided by 3 equals e to the 0.085t. Correct? You with me? I did a couple steps in one here.
Yeah.
In other words, I still set v of t equal to 1,000,000.
Right.
15,000 was the initial in both cases, so I got to divide 1,000,000 by 15,000. Now, what I was going to say about this answer here, that you came up with 46.691 years.
Yes.
You'd have gotten that exact same number if you'd have used common log of that divided by 2 times common log of that. In other words,
Okay.
log ratios are the same. Oddly enough, who knew? In other words, this is what I'm saying. The log of 5 divided by the log of 3 is the same as the common log of 5 divided by the common log of 3.
Okay.
Does not matter the base. As long as the base are the same, these ratios are always going to give you the same number. And that's why it doesn't really matter whether you use common log or natural log when you're solving these exponential equations. Natural log works very nicely, especially with the continuous one, because notice now when I take the natural log of both sides, you love it. You've got e when you're taking the natural log of e.
Right.
Because that just becomes 0.085t. So our answer here is that whole thing divided by 0.085. What number does that give you? Could be bigger than 46.
Yeah, 49.408 years.
And the only reason I knew it had to be bigger was from what we learned on number B, that even over a long period of time, Fund A outperforms Fund B.
Right.
So if it's outperforming it, it's going to reach $1 million sooner. But not by a lot, and that's just by about the right amount. Unless, of course, you're an old man and you die after 47 years, then you never see your money, huh? If you're in Fund B. All right, what else do you got?
So you mentioned this about Newton's rule, Newton's law of cooling. Oh, here, I'm sorry, it's a work problem. Let me send it to you real quick.
Okay. Newton's law of cooling, yeah, that's a logistic function.
Okay, I just sent it.
bet it came to my spam, no? Huh, I didn't get it this time. You send it to my email?
Yeah, the David Cohen 1949 at Gmail.
Yeah, the same one as the previous one. Previous one I got.
I'm gonna send it again.
David Cowan 1949 at gmail.com.
Yes.
Yeah, yesterday they were going to my spam, but the first one you sent today went to my regular one. I mean, it made it by the spam. Not this one. Just check and make sure that, no, that's the one we just did. Try sending it again if you would.
Yeah, sure thing.
There it is. And naturally they both come in at the same time.
Okay.
Huh. Wow. You have to do 16 also?
I do, yes.
Do 16 first.
Okay.
I'm going to have to get my book out and find Newton's law of cooling, the equation for that, to do that one.
Okay.
But 16 is a more common problem. Half-lives, very common when you're talking exponential decay. So let's look at that one, just because I know how to do it immediately. When it says the half-life of cobalt 60 is 5.3 years, that means that if you start with 100 grams, at the end of 5.3 years, you'll have 50 grams left.
Okay.
Okay? So, and radioactive decay is always continuous, where R is negative. So they say if you store 12.4 grams of cobalt today, what will it be 1 year from now? Well, you know how much you start with, but you don't know R. And you know T, but you don't know R. So you got to do some additional work here before we can figure out the answer to A. And here's the way I know how to do it. Your original amount is going to become half in 5.3 years, when T is 5.3, right?
Right.
That's what that says. In other words, if you know the half-life of something, you know that the starting amount, whatever it is going to become half of that at the end of the half-life year. And what this is going to allow me to do is solve for R, because notice the first thing that happens is you can divide both sides by P.
Okay.
Okay? Now, take natural log of both sides. So you have the natural log of 1/2 equals 5.3 R times the natural log of E, which is 1. So R equals natural log of 1/2 divided by 5.3. Okay? Now I have an exact equation. I know everything. The starting amount is 12.4 times E. Well, what is R? R is that number right there, and that is a negative number. So
Right.
I'm going to make it, I know it's a negative number because the natural log of a number less than 1 is negative. And question A says 1 year from now, so t is 1. So is all I have to do is figure out what that number is. Do that?
Yeah. $10.8799.
10.87 years?
No,
Oh, that's the amount you have at the end of 1 year. It's
Yes.
10.87 grams. Sorry. Lost track of what I was doing for a second. That makes sense. In other words, if 12.4 becomes 6.2 in 5 years, then in 1 year you're not gonna lose half, but you're gonna lose maybe 20% of it,
Right.
or not quite even 20%, more like 15%. So that makes sense, ballpark sense. Okay. Now, there's a couple of things you can do here. The way I did it is, to me, the perfect way. In other words, don't convert that to a decimal. Just because it reads a little nicer when you list what the exact equation for cobalt-60 is.
Okay.
Okay. And there's a T up there with that also. In other words, that's the exact equation. It's the amount of cobalt you'll have left is the amount you started with times E to the RT, and R is this natural log of 1/2 divided by 5.3.
Right.
That will be a negative number, and that's why you end up with less, because you have decay. When will only 3 grams be left? How am I going to solve that?
Set the equation equal to 3.
Yeah, let's get rid of all this stuff here. In other words, 3 equals 12.4 e to the natural log of 1/2 divided by 5.3 times t. This is the next step.
Divide by 12.4.
Okay. So now we got 3 divided by 12.4 equals all of that. What's the next step going to be?
Take the natural log of both sides.
Okay, so I'm going to take the natural log of that, the natural log of all of that. What does the right side become?
It becomes... Ooh.
Just the exponent. Circle it in red. That's what the right side becomes. Here,
Okay,
let me be clearer. Let me write it all out. So I'm taking the natural log of everything here. I'm taking the natural log of E, and it's being raised to the natural log of 1/2 divided by 5.3 times t.
right.
So now, using the properties of logs, I can take that entire thing and put it in front. And I'm left with natural log of E, which goes away. So, in other words, natural log of E is 1. So I can erase that, and that's what I've got.
Right.
The one on the left equals the one on the right. And now to solve for t, t equals this divided by this. And these can get a little hairy looking, but
Yeah.
that number should be in the neighborhood of 10 years. because what we're doing is cutting it in half twice, right? In other words, after 5.3 years, this 12.4 is going to be down to 6.2. And then after another 5.3 years, that 6.2 is going to be down to 3.1. So our answer better be 10.6 years plus a little bit.
Okay.
Did you come up with an answer? Can you do this in your calculator?
Yeah, it's 10.8508.
Perfect. 10.8508. They probably want you to round this off. I don't know. Did they give you round off instruction?
They did not.
Okay. All right. Now let's take a look at 15. Hold on a second. I gotta find Newton's law of cooling here. Ooh, I may have to. I may have to look it up in the index. Hold on a second.
Okay.
Figure out what page it's on. Newton's law of cooling, 307. All right. Here's what Newton's law of cooling says. The temperature, and this Newton's law of cooling is confusing because there's so many T's.
Right.
Is equal to the temperature T sub M,
Temperature of the medium.
the temperature of the surrounding medium, and then we've got a T sub O, which is the initial temperature of the object, minus T sub M, all to the, or times E to the negative KT. Okay, so once we have that formula, we should be able to just plug in here. Let's see what we've got. Look at this question.
What is K?
Find the decay constant. That's what K is.
Okay.
It's
So
similar to our R.
Right.
In other words, when we had cobalt 60 decaying, the decay rate was R, and we never actually put a number on it. We were using logs for everything. So I don't know what the decay rate of the cobalt is, but it's got to be pretty good. Oh yeah, we did figure it out because we figured out how much there was at the end of 1 year. The decay rate was about minus 15% for cobalt.
Yeah, negative 0.130782.
Yeah. For this, let's see. Read the whole problem here. Remove from the oven whose, so T sub M is 375. No, excuse me, T sub M is 68. T sub O is 375. And after 10 minutes, the temperature is 300. So that's going to allow us to solve for K. In other words, we know that the final temperature is 300 equals the temperature of the medium, which is 68, plus the original temperature was 375 when it came out of the oven, minus 68 times e to the minus k, and t is 10 minutes.
So for this equation, is t always in minutes?
Not always. T can be in any time unit you want for any of these equations.
Like PERT, it doesn't have to be in years for that? Or
No,
the compound?
no, there's things that have half-lives in seconds.
Okay.
Okay? And so T can be in anything. And T would typically, they'll tell you what T is in,
Right.
but it doesn't have to be years. It doesn't have to be anything. It can be in seconds, it can be in minutes, it can be in months. And depending on the substance, for instance, with radioactive decay, there are things that have half-lives of 2 seconds. And there's other things that have half-lives of 24,000 years.
Right.
That's why the nuclear bomb dropped on Hiroshima is so damaging, because it had such a long half-life. All that radioactivity doesn't go away. Only half of it goes away every 25,000 years. That's the half-life of it. So in 25,000 years from now, there'll be half as much as was there when the bomb was dropped, which means it's pretty uninhabitable forever. So half-life is a key concept in physics and decay, and T is not always in years.
So,
If we're in something other than years, then K is going to be different.
right.
Okay? So in this particular thing, I'm going to put T in minutes, because they said 10 minutes after it's removed, it's cooled off to 300 degrees. So the K that we calculate is going to be based on T being in minutes.
Okay.
Okay? So now all we have to do is solve this equation. There's only one variable in this equation, and that's K. And that's what they've asked us to solve for. Now, let's simplify this a little bit. We can certainly do that math. That's 307. So how do I solve this? I'll let you help me.
Subtract 68 from both sides, and you get 232 equals 307 times e to the negative k times 10. And then divide both sides by 307, and you said keep it as a fraction, correct?
Yeah.
Okay, so it's just 232 over 307.
Here's the problem with turning it into a decimal. Is if you turn it into a decimal now, you got to round it off to some number of places. Right? And then we're going to have division by e to solve for k at some point. No, I guess we're not. But you can accumulate round-off error. And so it's okay, if you're going to round something off to a decimal, always wait till the final step if you can. Okay? And I can here, because I can leave this as a fraction. Now I'm going to take the natural log of both sides. And what's left on the right is minus 10k equals that quantity there, which is a negative number. And so k is going to be equal to that.
Right.
Now, that'll make k positive. But that's what you want, is a positive k, because notice that there is a negative sign in front of it now. So you want k to end up being positive, because you're always talking about a decreasing temperature here. This is Newton's law of cooling, not heating. So the temperature is always dropping.
Right.
Which means K, that's why there's a negative sign in front of it, the K, for the general equation. This is the general equation. This is Newton's law of cooling equation. And it's always a negative, and then the K always ends up being a positive number, so that the cooling will be negative.
Okay.
Okay. I'm surprised he didn't give you this, or did he? No, he didn't. He didn't on the paper, which is peculiar. I don't know of too many pre-calc classes where they expect you to memorize Newton's law of cooling. Oh, and this does ask it to the nearest 4 decimal places.
Yeah.
It says use Newton's law of cooling to answer the following questions, but it doesn't give you the master formula.
Yeah.
That's odd. Did he really expect you to memorize it?
I think she does, yeah.
Okay. And now we can answer B because we've solved for K. Why don't you come up with a K, and we'll finish this problem in about 6 minutes.
0.0280.
So K is 0.0, what again? I'm sorry?
0.028.
To 4 decimal places. That's to 3.
Sorry, 0.0280.
And then you round it off to get that 0?
No, it was at 0.028011.
Okay.
So
yeah, that's correct.
Yeah.
You rounded it off. Okay. Okay. And so there is our equation that corresponds to this model. Not everything is going to be like a loaf of bread. If you had a jar of metal that was in that oven, it's not going to cool off at the same rate as this loaf of bread is. So anything else is going to have a different K. In other words, I call the original equation that I wrote the general equation for Newton's law of cooling, whereas this equation is the specific equation for this particular situation only. In other words, K only applies to this loaf of bread. Now, part B, use your model to determine how long it will take until the temperature is 100 degrees Fahrenheit. Well, so what do I need to do now?
Set the general equation equal to 100.
Well, not the general, but the specific.
Right.
We're now looking at the specific equation that only applies to this loaf of bread. But you're right, I'm going to make that 100. There's only one variable there. It's t.
Yes.
And it's in the exponent, so we're going to use exactly the same process that we've been using to solve for variables that are, or exponential equations, which is to isolate that as much as we can, and then take the natural log of both sides.
Right.
And it's important to know that that t will be in minutes. because this specific equation is based on T being in minutes, and in fact it's based on T being in minutes and all of our temperatures being in Fahrenheit.
Right.
You make all the temperatures in Celsius and we'd end up with a different K. Or if you make T in hours, we'd end up with a different K. So when you solve this equation here, the answer you get is going to be number of minutes. And, you know, you can use the ballpark analysis on this also. In other words, if it cooled off from 375 to 310 minutes, it's got another 3 times that much cooling to do. So our answer should be in the neighborhood of 30 minutes, but it's not linear, obviously. It's actually a logistic function. So it's not a straight linear relationship. I can't say that because it cooled off by 75 degrees in 10 minutes, that it's going to cool off another 200 degrees in 30 more minutes. Can't say that. But you can certainly solve this. What'd you get for T?
80.754 minutes.
Yeah, in fact, you can see it's definitely not linear.
Yeah.
It took 10 minutes to cool off by 75 degrees, but then another 70 minutes to cool off by another 200 degrees. All right. Sounds like a good place to stop.
Great.
All right.
Thank you very much.
You're welcome, and I will talk to you tomorrow. Let me just verify our time, 8 o'clock tomorrow night.
Yes.
Talk to you then, William.
Great. Thank you very much.
Bye-bye.